Okay, so we've defined the scalar product for vectors. Now we're going to define a different mathematical definition called the vector product, also given the name the cross product. This has a somewhat more complicated definition. Just in terms of notation, we'll denote the vector product or the cross product with a big cross symbol. Right? So A cross B will be telling you that you need to calculate the vector product. And this is the definition. We can see it's returning a vector. I have some components I hat, component j hat plus component k hat. So unlike the scalar product, which returns a number, the vector product returns a vector. Okay, we can see that calculating the components of this vector A cross B is a somewhat complicated grouping of the components of the individual vector components of A and B. But you can always plug into the formula and calculate the cross product. But let's try to more focus on the concept of the cross product, and we're probably going to be calculating the magnitude of this vector more often than we are going to be using this formula. Okay. The most important thing we can know about the cross product is it's going to return a vector which is perpendicular to both A and B. So if I calculate the cross product of A and B, the cross product vector is going to be perpendicular to both individually A and B. Right? So if I have some vector A and some vector B, the cross product is going to be pointing in this direction. You can see it's kind of perpendicular to A and perpendicular to B. So we need 3 dimensions to really draw a cross product vector. But a little bit more simply, A cross B is a vector which points in the direction given by the right-hand rule, so we'll talk about that in the next slide. But this is just a method to easily figure out which direction this vector points. And the magnitude of this vector is given by this definition, which is a lot simpler than what we had up here, right? The magnitude of this vector A cross B, or the length of this vector, is just the magnitude of A times the magnitude of B times this time the sine of the angle between them. If you recall, the dot product was defined with a cosine between the two vectors. In this case, we're defining it with a sine between the two vectors. Okay, so the right-hand rule, if I want to calculate A cross B, and I have a little picture here of A cross B, the way I like to do it is with my entire hand. Some people use it with just 3 fingers. I prefer using my whole hand. I point my fingers in the direction of vector A. So all 4 of my kind of pointer fingers, I point in the direction of A. And then I curl my entire hand in the direction of B, and now my thumb is pointing up in that direction given by this purple arrow here, A cross B. Okay, so my fingers only curl in one direction, so I point my fingers in the direction of A. I can curl them towards B, and my thumb is going to point in this direction now. If I wanted to calculate instead B cross A, right, this time I point my fingers in the direction of vector B. Right, but if I want to curl my hand towards vector A, I need to turn my hand around, right? Because my fingers only curl in one direction. So I curl B towards A, my thumb is now pointing down along this purple arrow here. So you can see that B cross A gives you a different answer than A cross B. In fact, B cross A is equal to minus A cross B. So they're going to have the same magnitude but point in opposite directions. Okay. So that's the vector product in the right-hand rule. Again, we need to ask, why are we defining this mathematical concept? What is the point of doing this? The vector product, it turns out, is going to measure how perpendicular 2 vectors are, and it's going to really help us define real-world concepts like torque. Right? If I want to turn this wrench, I need to apply a force on that wrench, and I need to apply that force in a particular way in order to create torque in order to turn this wrench, to turn this bolt. Okay, so we'll talk more about that on the next slide. So particularly with torque, we're going to define it in this way. The magnitude of our torque is going to be given by R cross F, where R is a position vector drawn from the axis of rotation to where our force is applied, and the force is going to then, again, be applied by there. And so if I want to turn this wrench, I could apply a force at this location in this direction, and that's going to give me torque, because by this definition, RF sine phi, where phi is the angle between these 2 vectors, sine of 90 degrees is equal to 1. Right? So this is just going to be R times F. That's going to be a large number. I'm going to get some torque. We're going to turn the wrench. Right? If I was to apply the same force, but just in a different direction from the same point, I wouldn't get as much torque. Right? If I'm applying this force in this direction, well, this force has some component which is down towards that bolt, and that's just pushing on the bolt, right? That's not going to make that bolt turn. It's only this component of the force in this direction perpendicular to this r vector, which is going to make that wrench turn. So this is going to give me less torque. In fact, I do sine of 30 degrees here. Sine of 30 degrees is 0.5. So even if this is the same amount of force as this, I'm going to get half the torque, right? Even though I'm applying the same force to the same location, I'm applying it in a different direction, and I'm getting less torque. So I hope that communicates why we need to define this. Finally, I could apply my force at the same location with the same magnitude, but I could put it in this direction, right? And in this case, R and F are parallel. Sine of 0 degrees is 0, right? So that's 0 torque, right? So when I have two vectors which are parallel, their cross product is going to be 0, and you can see that's important for defining torque, because even though it doesn't matter how big this force is, I'm never going to turn the wrench with this force. So the direction of your force matters. So if we want to write down a mathematical definition to communicate this fact that the direction of your force matters when trying to make something turn, we need to use the cross product to do that. Okay. What about understanding a little bit more conceptually why we define the right-hand rule for the direction of torque? To do that, let's talk about something more in 3 dimensions here. So here we have a wheel. It's kind of free to rotate in the XY plane, so it has some axis along the Z axis here. And I want to apply this force at the edge of the wheel, and that's going to apply a torque, and that's going to make the wheel spin in this direction. Right? If I apply a force in this direction, the wheel is going to spin in this direction. So how do we define that direction? I want to mathematically tell you which direction I'm making that wheel turn. It turns out, the way we would typically say that something is turning was clockwise or counterclockwise, but that's not a very good mathematical definition, because that depends on your perspective. If I'm looking down on the wheel is kind of turning in this direction, so it looks to be spinning clockwise. But if I was down here, kind of underneath the wheel looking up, the wheel would be spinning counterclockwise from my perspective. So that's ambiguous. We don't want that mathematically. We can't do that. Right? So instead, we define torque with the right-hand rule. I put my hand in the direction of R, curl it in the direction of F, and my thumb is pointing down. Right? So we're going to define torque to be, in this case, the direction of minus Z. It's going to be kind of along the axis of rotation, but in the minus Z direction. Right? And that is just removes all the ambiguity. If everybody just decides we're all going to use the right-hand rule, we can always define the torque direction, which is going to tell us which direction we're going to make the wheel spin with that torque. All right, so that's why we have to define this mathematical concept. If I applied that force in the opposite direction and tried to make the wheel spin in the opposite direction, now I do the right-hand rule, R cross F, my thumb is pointing up in the plus Z direction. Right? And so in this case, my torque is pointing in the plus Z direction, and that's just our mathematical way of communicating in an unambiguous way which direction our torque is. It turns out when we get to rotation chapters, all of our vectors are going to be pointing along the axis of rotation, because that's really the only way to define them in an unambiguous way. So please let me know if you have any questions on the cross product.